Hello again, welcome to the Renewable Energy Technology course, and this is the micro and small hydropower series, and this is 1.2 series dealing with the micro small hydro design guidelines. In the previous session we discussed about the historical development of hydropower and look at the potential of hydropower and also look at the components of hydropower. Now, in this session, I will just give a brief description of components once again. The basic components with the hydropowers is the weir and intake, gravel trap, header's canal, descending basin, forward tank, and you have penstock pipe, and then the powerhouse and the tailless canal. Now, we will talk more about each component's design guidelines. You can see one of the projects that has been constructed and which I was engaged in 2004, and this was the project for electrifying the hospital electrifications in Lukla in Nepal, and this was 25 kilowatt projects. And you can see here this one is the intake locations, and this one is the forward tank, and you can see the penstock pipe alignment, and you can see here the penstock pipe alignment along with the powerhouse, and also you can see the spillway coming here, and this is the turbine coupled with generator. Now, we will talk more on design aspects of intake. So, while designing the micro hydro or small hydro, you can have an intake, either you can have a side intake or you can have a bottom intake. Normally, rectangular orifice type intake is preferred, and orifice should be fully immersed in the water in order to assure the design flow. And normally, this side intakes are coupled with gravel trap, and you can see in this drawing here you can see the normal river level and design flood level, and here you can see the baffle wall to protect the structure from the design flood level, and there is a orifice which is basically the inlet for the water going inside the gravel trap, and a cross trash track is placed in an inclined position so that it can protect the water coming in from the debris. So, it will not allow debris to enter inside the intake structure, and there is a sluice gate to control the flow. And in the gravel trap, as I said previously, the main function of the gravel trap is to trap the gravel particles here, and once the gravel particle is of a certain volume, then you can use this flushing gate to flush out the gravel from the gravel trap. And mostly the bottom intake is this kind of intake is called bottom intake, and bottom intakes may be selected where there is no significant sediment movement along the river bed, and if the river slope is steep, then in that case you use bottom intake. And as I said earlier, a cross track, sluice gate and a spillway are provided in the intake. And normally you have to take more water in the intake, at least the water when you design the intake, the design flow should be at least 10 to 20% more than the design flow for the turbine. Also, we should think of how to select the location for the intake, and if there is a river bend, then the intake should be at the out bend of the river to limit the sediment deposition and also to ensure the flow availability during the dry season. And if you have a big boulders, and there is vegetations in those areas are preferable to select as intake because it can provide natural protection to the intake structure. The second one here is the header's canal, and as a header's canal you can use pipe structure, header's pipe, or you can make stone masonry canal or cement masonry, concrete masonry canal depending upon the size of the flow. And also selection of header's either whether pipe or canal depends upon the slope of the profile. What is the land profile is there. If the land profile is steep, then in that case header's pipe is preferable, and if the land profile is mild or moderate slope, then header's canal is economical and also preferable to construct with the local materials. And also we have to think about the velocity in the header's canal, because we don't want to erode the canal. At the same time, we don't want to store the sediment in the canal. So we maintain the velocity in such a way that the water carries the sediment along with itself, and only will deposit these sediments in the descending basin. So the minimum velocity maintained in the canals is 0.3 meter per second. Here you can see the drawing of a header's canal, and this is a normal water label, design normal water label, and this is a stone masonry canal with the 1:4 cement sand mortar. And while designing this kind of canal, we should also provide some free space, which is also known as freeboard, and this is basically provided to allow some fluctuation in the flow in the canal, and this minimum freeboard should be either 300 mm or the half of the water depth. That is, here you can see S is the water depth, so S by 2 of the water level. Which one is the minimum? You choose that one as a freeboard here. So H1 should be either 300 mm or S by 2, whichever is the lower one. And also, if you have a long canal, there might be some places where the boulders and also comes, or maybe some kind of obstruction can arise in the future. If there is some unstable places is there, as far as possible we avoid the channel going through that. Otherwise, we have to provide some spillway or skips, so that the water, if something happens with the canal and water is blocked, then the water is safely transferred to the river through the spillway. So we just don't destroy or destruct the canal structures there. Now another important structure is the desilting basin, and this desilting basin is the main function of this desilting basin is to settle down the silt particles that has been carried by the water. And if you look at this drawing, this is the plan of the desilting basin, and this is the sectional view at AA of the desilting basin. And in the upper part of this inlet of the descending basins, we try to gradually increase the width of the canal, and the main purpose of this is we want to give the gradual settlement of the particles in the desilting basin. So we want to gradually reduce the velocity of the water and then settle down the particles that have been carried by the water in the desilting basin. And this is the settling zone where all the sediment are deposited. And then again you have this outlet channel, which is again have a contraction of 2:1. And we also have flushing gate to flush the sediment deposited on this, and also we provide spillway if excess water is coming in the desilting basin. So we have different heads projects, and based on that we also have to think about what can the silt particles impact on the turbine. So if you have a high head, the risk is high with the silt going into the turbine. That's why if you have higher head, then we try to settle down the particle size of 0.2 mm, and we design the desilting basin accordingly. And if you have head less than 100 meters, then we try to settle down the particle size of 2.3 and above. And if you have only head around 10 meters, then we are less concerned about these particles, and we try to settle down the particle size from 0.3 to 0.5 mm or greater size. Now I would like to talk about sizing the penstock. How do you design a penstock, or how do you select the diameter of the penstock? I'll just want to start with an example here. Let's talk about a power plant having 15 meters of length with a design flow of 2 meter cube and gross height of 9 meters. And let's say the penstock pipe is the mild steel pipe has been recommended, and from the Manning's coefficient, the roughness coefficient of this particular mild steel pipe is 0.012. Now we can determine the head, we can determine the diameter of the penstock pipe by using the area of velocity and the relation with the area of velocity and the flow. And the diameter of penstock pipe can be given by some constant times design discharge divided by the velocity to the power 0.5, and the constant is basically 4 by pi, and the velocity can be chosen from 1 to 2.8 meter per second, and we have particularly in this case we have chosen 1.6 meter per second, and by with all these values, if you calculate the diameter of penstock pipe, it will come around 1.26 meter. Now the next thing after calculating the diameter size is to see how much head loss will be there if you choose this penstock pipe. So maybe if you have a shorter length of the pipe, then maybe this will work, this calculation will work. But if you have a longer head, then maybe longer distance, longer length and longer head, then might be this particular selected diameter might not work. So in that case, we need to check with the head loss with the given diameter. So we check with the frictional losses in the penstock pipe, and we use again the Manning's formula to calculate the head loss. And after calculating the head loss, we found that the head loss is 0.114 meters, which is 1.27% of the total gross head. So which is in the safe region, that is normally we try to keep the head loss around 5 to 10%, and it is below 5%, which is in the recommendable range. So with this, I would like to end the first part of this micro and small hydro component design guidelines, and in the next session I will talk more about the designing and selection of the turbine, generator and electronic load controller or the governor in the hydropower system. Thank you.